normal stress, which we know better as pressure, and shear stress, which is due to viscous effects due to relative motion. So very briefly, I'm not going to go back all the way through this, but we said, all right, if you've got a little chunk of a surface that has a surface area dA, and we assume it's got some amount of pressure force acting on it, okay, PdA, and it's got some shear force acting on it, tau times dA. Okay, those being oriented on the surfaces, along the surfaces, normal and tangential coordinates. All right, the result of these two is going to be some resultant force, F. And if we integrated, okay, all of the little, or call this dF because it's a small elemental contribution, but if we integrated all these dFs around all of the different little dAs making up the surface area of an object, we would get that the total force is equal to, the integral over the surface area of dF, which is the integral over the surface area of tau omega times the tangential coordinate plus integral over the surface area of negative p dot n dA. And then we said, well, we could take, we said that the tangential and the normal coordinates really can each be written in terms of the x and the y components of a global xy coordinate system, right? Said, so if we've got x and we've got y, then we can take direction cosines, and I'm going to skip this part, but the idea was we could rewrite this entire integral in terms of the components that were perpendicular to the flow plus the components of the force that were parallel to the flow. Same force, we're just recasting in terms of new vector coordinates. Okay, it's a change of basis. And we named this integral of all the forces that occur perpendicular to the flow. We called this the lift, and the second one with all the forces parallel to the direction of flow, the drag. Okay. In this case, we're assuming that I guess we didn't make any assumptions, but we can assume that the flow is being defined by some uniform upstream flow direction. So it's very rare that we have the kind of detailed information, and I specified this last time. It's very rare that we have the detailed information necessary to actually carry out this integral directly. So it's far more common Our solution to this is to use much more common tabulations of lift and drag, both subjected to dimensional analysis. Which gives us the lift coefficient, which is equal to lift over 1/2 rho u squared times a, and CD, which is the drag coefficient, which is drag over the same 1/2 rho u squared a. Okay, and in both of these, so let's go. Lift coefficient and the drag coefficient. And if we went ahead and did a dimensional analysis on the CL and CD terms, we would see that in both cases there are dimensionless. We can do that really quickly, from Bernoulli's equation, this 1/2 rho u squared, we recognize that that's going to act like a pressure, This is what we would call dynamic pressure. This is Bernoulli's equation. So pressure times an area gives you a force. You have a force over a force. Everything cancels out. In these cases, A is defined as a a reference area, and will be given in the problem that whatever problem you're considering. Okay, it's usually taken to be the projected area, either the projected area, the silhouette area of an object when viewed from the direction of the flow, or it is the total surface area of an object. And like I said, that will be specified. So we've got CL and CD, and the idea now is that these values of CL or CD are typically had from either extensive tabulations, lists, tables, simplified theory, which isn't really our thing in this class, or numerical simulations. Okay. So we're going to concentrate today on the second of these, on drag, and then we'll loop back and hit lift in the next lecture. So we've seen, right, that I'm going to write out the full expression for drag. We saw earlier that drag is equal to the integral of shear stress sine theta dA plus integral of P, or I should say minus P, cosine of theta A. Nope, that is going to be a plus P. And this first term, right, the one involving the shear stress, we're going to call this d sub f. And the second term, we're going to call d sub p. Okay. Friction drag and pressure, or what's known as form drag. Okay, so what we're saying is that the contributions to drag are, again, shear stresses and pressures. And so if we keep those two separate, we can understand that the friction drag itself, right, by its name, is composed entirely of the shear stresses around the surface. And the pressure drags can be due to the imbalance of pressures, in front of and behind an object. Likewise, we could non-dimensionalize so we get that the total drag coefficient is equal to CDF plus CDP, right? Which we keep the same nomenclature, our friction drag coefficient and our pressure drag coefficient. So the drag itself, and by extension the constituent frictional and pressure drags, are functions of, and we talked about this before as well, really two principal things. Okay, body shape and Reynolds number. Okay, they're due to they're dependent on a lot of other stuff as well, Mach number, Weber number, all of these other different factors in a problem, but we're going to concentrate on these two principal ones. So I'm going to pull up the slide that we used one of our earlier lectures. Here we go. Where I said, all right, the external flow around an object is highly dependent upon, like I said, Reynolds number and the shape of that object. And we divided these shapes into two kind of families. The ones on the left, what we call streamlined shapes, and the ones on the right, what we call bluff bodies. Let's see, I get my pen and color. Streamlined and bluff. And there's a primary distinction between a streamlined body and a bluff body is that a streamlined body, right, as the name implies, the streamlines in the flow generally contour very closely to the body. They're not deflected very much. Whereas with the bluff body, they deflect. And more importantly, on bluff bodies, we have what's called separation. We'll talk about this a little bit more in a few minutes. But the idea is that when these streamlines have to deflect, there's some energy being lost here, so they're not able to actually stick to the backside of the body. So they detach, leaving what's called a viscous wake behind them. And this happens, there's no hard cutoff for what makes a bluff body a bluff body, but things like cylindrical cylinders, cubes, okay, anything that really lacks the behaviors of a streamlined body are bluff. And in both cases, the effect of Reynolds number is that as the Reynolds number increases, okay, the viscous effects in the flow get smaller. So these gray shaded regions where we say the viscosity here is important, and we say that by setting some criterion that the velocity of the flow is less than 99% of the free stream flow. Okay, that shrinks closer and closer to the body as the Reynolds number increases from the top to the bottom. So just like we said, this character of the flow, the way the flow looks, is dependent upon these two factors. The drag is also dependent upon these two factors. So at low Reynolds numbers, okay, around like with those figures up at the top, the drag is going to be mostly dependent. So at low Reynolds numbers, the drag is highly dependent on the value of the Reynolds number. Okay. And then at moderate Reynolds numbers, the drag is dependent upon both the value of the Reynolds number and the shape of the body. And at large Reynolds numbers, drag is dominated by the shape. And we can kind of see that, right? In this top row, you'll notice that the flow around the cylinder, it doesn't have that separation region. So the flow around the flat plate, which is our ultimate sort of streamlined body, and the bluff body, they're different, right? Because the amount of deflection of the streamlines, but neither one of them has pronounced flow separation. So the flow is being dominated by viscosity. Viscosity, right, is the hallmark of the Reynolds number. Here, we do see some effects of the body shape starting to creep in. We can see a large region of the flow still dominated by viscosity, and at large Reynolds numbers, in both cases, the viscous effects, okay, have shrunk down to a pretty small region. So that Reynolds number dependency, as the Reynolds number increases further, this region is going to get asymptotically smaller, but it's a far cry from the difference between that and that. All right. But the pronounced difference in this case is that even though this one has a thin boundary layer, now we have this big messy region of flow behind it. Okay, I've beaten this horse to death. Let's move on. So let's talk first about the effects of shape all by themselves. So the effects of shape on, this will work. This is not going to play. There we go. So the effects of shape are fairly obvious when you start looking at the way that flows behave. Okay, if you have something that's a flat plate sort of face onto the flow, it can be thought of as kind of the ultimate bluff body. What you can see is that very clearly defined flow separation occurring behind it. In fact, if you were to try to calculate the shear stresses on this and figure out how much of that drag was made up of frictional drag and how much of pressure drag, what you would find is, okay, in order for frictional drag to be developed, there has to be some flow creating shear stresses that are in the direction of the flow, right? The only place that can occur is these little outer edges, right? So there's going to be very little friction drag, but you're going to have a really high pressure here and a really low pressure here that's going to try to tend to suck that disk in the direction of flow, creating pressure gradient. So this is a case where the drag is going to be primarily pressure and only minimally due to friction. Another example I like here is these indoor sort of skydiving trainers, where simply by modifying, actively modifying the shape or the profile that one presents to the oncoming flow, they're able to modify their drag coefficient fairly actively. They essentially streamline themselves in order to minimize their drag and spread out, become as bluff as possible to maximize their drag in order to control their altitude. You know what? I'm going to skip that. And we're going to jump back over to the slides really quickly, after all. So the effects of the shape of an object are largely captured through these tabulated lists of drag coefficients. Okay, and these are figures that are all in your books, 928, 929, and 930 over on the right. But remember I said at large Reynolds numbers, the drag coefficient is mostly a function of shape, and that's what's reflected in here. In fact, you've got a bunch of columns, okay? And I want to kind of move from right to left. The rightmost column gives you the value of a Reynolds number that is considered sufficiently high, okay, that the Reynolds number is no longer an important factor. Okay, so if you're considering the flow around a bar with a hexagonal section, as long as the Reynolds number is greater than 10,000, the drag coefficient in this table is not going to change much. Okay, if it's 1 million, if it's 10 million, it's going to remain substantially the same. This column right here actually gives you the values of the drag coefficient. And in some cases, there are going to be a range of values. So if you're talking about a rectangle, okay, the aspect ratio of that rectangle, that is its width over its height, is going to dictate what the drag coefficient is. And in other cases, such as an angle or a semicircular cylinder, the direction of the flow past that object is going to dictate the drag coefficient. Okay. In this second column here, I mentioned that you'll be given or you'll have some way of looking up what the reference area that you're supposed to plug into that drag coefficient is. And that's what's given in here. So if we're talking about a rectangle, B times D. So the height times the distance of that rectangular section into the page. All right. And so for most of these drag values, you'll find that, like I said, if you were to situate yourself so you were staring in the direction of flow and sort of measure the area of the silhouette or the profile of that object, that is almost always going to be the area that you find in these. So we've got two-dimensional sections here. Okay, so these are things where you'd be expected to extrude them out of the page. We've got three-dimensional objects, like cones, circular rods, or discs, and then we've got some more sort of unusual or biological objects here, such as a standing person, a person standing, sitting, and crouching, parachutes, satellite dishes, what have you. So this table is going to be sort of your primary tool in calculating drag coefficients on objects. Let's do a quick example with it. And I should mention that the CD values that are given in this table, this is the sum of the frictional drag and the profile drag for all of these objects. All right, so let's consider a building is located on a flat expanse of ground with absolutely nothing for miles around. Okay. And let's assume that this building is cubic in shape, so that is, it has dimensions of 30 meters in depth, breadth, and height. And it's subjected to a uniform wind speed of 10 meters per second. And we're going to assume here that the air has a kinematic viscosity, okay, nu, of 1.5 times 10 to the negative fifth meters squared per second. And the density is 1.23 kilograms per meter cubed. So in this case, we're asked to find simply what's the wind load on the building. Okay. What is the force going to be on the building exerted by this 10 meter per second wind? So first step in this solution is going to be see if there's an entry in that table I just showed you. So let's pull that up for a moment. Look at this. Right here, we've got a cube, okay, with a side length of d, in this case d being 30 meters. So we've got a couple useful things here. The projected area should be taken as d squared. Again, it's going to be the frontal area of the building. And as long as the Reynolds number is greater than 10,000, our drag coefficient should be 1.05. So our process in this problem should be to calculate the Reynolds number, see whether it satisfies that criterion of being greater than 10,000. If so, then the drag coefficient can be taken to be 1.05, and we simply take the parameters of the problem and redimensionalize that drag coefficient into a dimensional drag value. So the Reynolds number, when I should mention actually that the definition of the Reynolds number is going to be given here as well. If I zoom in, you can see that the Reynolds number is rho u d over mu. So it's going to be, which is also equal to u d over kinematic viscosity, right? Where d is that side length of the building, at 30 meters. So u d over mu, which is 10 meters per second times 30 meters over that 1.5 times 10 to the negative fifth meters squared per second. And this is going to give us a value of 2 times 10 to the seventh. All right, so 20 million. Clearly a lot larger than that criterion, that minimum of 10,000 that was included in the table. So the Reynolds number is large enough that we can say drag coefficient is equal to 1.05, okay, which is the value in that table. So then the drag is going to be equal to, well, we'll say, so this is right, d over 1/2 rho u squared times d squared. So we can find the drag then as cd times 1/2 rho u squared times d squared. Well, confusing my d's. Yep, d squared. 1.05 times 0.5 times 1.23 kilograms per cubic meter times 10 meters per second squared times 30 meters squared. And if we plug all those values in, we should get 58,100 newtons. Okay, so calculating drag is really as simple as that. It's looking up a value on a table, making sure that you have a sufficiently high Reynolds number, and running with it. And for most engineering problems, okay, most things involving flow of water and flow of air, Reynolds numbers tend to be pretty high. And so you're usually safe using those drag coefficients. There are cases where at lower Reynolds numbers, you do have to be conscious of what the values of those Reynolds numbers are. And so let's pull this up. So elsewhere in your table, or elsewhere in your book, I should say, you have now low Reynolds number drag coefficients. And what here you'll notice here is that the value of those drag coefficients is highly dependent on the Reynolds number. Okay, it's inversely proportional to the Reynolds number, but not nearly as dependent on the actual shape of the object. Okay, so a circular disk normal to the flow relative to a hemisphere relative to a sphere, they're off by, it's a 20.4 over Reynolds number up to a 24 over Reynolds number. So it's not super shape dependent, but it is highly Reynolds number dependent. And so if your Reynolds number is not sufficiently high to use those tables, then check, is it really low? Okay. And so these are valid for Reynolds numbers that are smaller than 1. And that's what qualifies as a very, very small Reynolds number. Things between those, between 1 and like 10,000, usually it's going to be very shape dependent and very Reynolds number dependent. And so that's leading us to next, our last example, and we're going to have to move through this pretty quickly. This idea of separation. Okay, so I talked about how separation occurs on bluff bodies. The thing is, and we talked about how laminar and turbulent flow are functions of the Reynolds number. When you exceed a certain Reynolds number, the flow goes from laminar to turbulence. What I did not get a chance to tell you about, though, is how that turbulent flow, laminar versus turbulent flow, affects the flow around bluff bodies. So I want you to consider a boundary layer that's attached to a bluff object. Now, if I'm a particle at point A, okay, I hit that leading edge of body and I start to go around. Okay, and that's generally going to create some acceleration of the flow. The flow is going to speed up as it's squeezed around the outside of that body. Okay, now, Bernoulli tells us that as the flow speeds up, what happens to the pressure? It drops. Okay, so when you hit point C there, that's usually going to be the point of minimum pressure, maximum velocity. Now, if the flow didn't have any viscosity, if it were perfectly inviscid, lossless, Bernoulli would tell us that from point C to point F, it would then slow down again and regain all of that pressure. Basically a perfect energy balance. However, the boundary layer is this sort of energy-robbing, heat-generating nuisance that turns some of the kinetic energy of the fluid into thermal energy that's not recoverable. So now if I'm a particle at point C, and I march along to point D, I would like to slow down and have the pressure increase, but some of the energy necessary to do that has been turned into heat. And so the flow is going to be decelerating, and the pressure is going to be increasing, but at some point the flow has been slowed down enough that it comes to a stop. So at point D, let's say the flow has stopped, but the pressure in front of the flow is still greater than the pressure behind it. Okay, so the only logical next step is for the flow to head back upstream, and that's what we call flow reversal. And that's what happens on a bluff object. Around point D to E, flow hits a point where it's stopped and the pressure is still increasing in the direction it wants to go, so it has no choice but to turn around and go back the direction it came. So you get these recirculating regions of flow separation. Now when the flow is turbulent, I talked about how turbulence is much good at mixing momentum from further out in the flow, closer to the body. What that does is it sort of mixes in some more kinetic energy, so the flow can remain attached for longer than can laminar flow. So this is a flow visualization I did in a water tunnel where they seeded some hydrogen bubbles into the flow. And on the left is laminar flow. So you can see that detachment point occurring at, right around the halfway point. Okay, fairly close to 90 degrees. And then here's turbulent flow, where that flow separation isn't occurring until right around here. The advantage there is that wake, when you have flow separation, the wake that occurs behind that is this low pressure region, and it tends to increase the amount of pressure drag. So the kicker is that turbulent flow is actually much better, or it actually reduces the drag coefficient of a body when it's a bluff body. Okay. Turbulent flow is lossier. We talked about that. The drag coefficients in turbulent flows due to friction are higher. So you're paying some penalty if you have turbulent flow. You're paying some penalty in terms of the shear stress, okay, that friction drag. But you're saving so much drag in the pressure drag because you've minimized the region of this low pressure wake that you make up for. So that leads to one of the kind of the crowning achievements of fluid mechanics, which is the golf ball. I want to talk about this very briefly. So shown here is like a smooth, I want to concentrate on a smooth sphere here. Right, so shown on the x-axis is the Reynolds number from 0.1 to 1 to 10, there's a log scale. And we can see it starts out really, really highly dependent on the Reynolds number, okay, for this sphere. And at some point around 1,000, it stops being so dependent on Reynolds number. Okay, then we hit a Reynolds number around 200,000. Yep. And it goes through what we call the drag crisis in fluid mechanics. Basically, the flow becomes turbulent. That region of flow separation shrinks up, and the drag drops. Okay. So this tells us, oh man, we actually, like, if we want to minimize the drag on something like a ball, it has to go really fast, okay, in order to promote turbulence. The other option is to add some sort of texturing to the surface. And so if we consider now, here's a zoomed in portion, where here's our smooth sphere, being our drag coefficient, it's a function around this number. We've got that same drag crisis we saw, but if we were to add some sort of dimpling, okay, with some height of epsilon, we see that we move that drop, that Reynolds number, at which transition to turbulence occurs, to lower and lower Reynolds numbers. So you've got our conventional golf ball, and you see you hit turbulence, and therefore that minimization of pressure drag pretty early on. So the idea here is when you hit a golf ball, if it's a well-hit golf ball, your Reynolds number, the velocity, is going to give you a Reynolds number that's somewhere right around here. So if that golf ball were smooth, you would be paying a really large drag penalty because the flow is still laminar. But by dimpling it sufficiently to promote turbulence, you've actually minimized the amount of drag. That's why a dimpled golf ball will actually fly further and faster than a smooth one. And I've got an example on this. We don't have time to go over it now, but we'll talk about it at the beginning of the next class. I'll see you guys on Wednesday. Please remember to, if you haven't finished yet or haven't done so yet, please submit those ACE evaluations.